Welcome to this explainer. Today we're diving straight into a really beautiful part of middle school math. We're going to focus on explaining a fascinating chapter that literally takes us by the hand and transitions us from those simple, everyday arithmetic observations, the little numerical quirks we've all noticed, straight into rock-solid, undeniable algebraic proofs. Think of it like upgrading your mathematical tool belt from a basic magnifying glass to a high-powered microscope. It's going to be a lot of fun. We'll kick things off with a central mystery. This was actually posed by a student named Anshu in the textbook we're exploring today. Anshu asked, can I write every natural number as a sum of consecutive numbers? What about zero? Or even numbers? I absolutely love starting here because, let's be real, true math doesn't start with an answer key at the back of a workbook. It starts with curiosity. It starts with a simple what if that spirals into a much deeper investigation. Here's our roadmap for the explainer today. We're going from section 1, posing mathematical questions, to 2, proving patterns with algebra, then 3, properties of divisibility, 4, mapping multiples, and finally 5, the divisibility table. All right, let's jump right into section 1, posing mathematical questions. I absolutely love this quote straight from the chapter because it brilliantly hits the nail on the head about a core truth that often gets lost in the classroom. Math isn't just about memorizing arbitrary rules. Wondering and posing questions and conjectures is as much a part of mathematics as problem solving. When you wonder, you literally open the door to discovery. Let's look at Anshu's consecutive numbers puzzle to see this in action. Try this. Take any 4 consecutive numbers. The example here uses 3, 4, 5, and 6. Now place plus and minus signs between them in every combination you can think of and evaluate the results. If we walk through this concrete exercise, we quickly start to spot some really intriguing patterns. Certain sums just keep popping up no matter which sequence of 4 numbers you originally picked. It feels a bit like magic, but we know it's math. So the real question is, why does it happen? But how do we know these patterns are always true and not just some random coincidence? Well, that brings us to section 2, proving patterns with algebra. Take a look at how these two methods compare. Over on the left, we've got an arithmetic example. If we plug in specific numbers like m equals 1 and q equals 2, we get 8, which is an even number. That's great, right? But it only proves it for the numbers 1 and 2. Now look at the right side. This is our algebraic proof. We take the general expression 4m plus 2q and just factor out a 2. We get 2 times the quantity of 2m plus q. By using algebra to bridge the gap from specific, isolated numbers to a universal proof, we show that factoring out that 2 absolutely guarantees an even number result, no matter what whole numbers you plug in for m and q. We've officially moved from I think so to I know so. And we can actually apply this exact same generalized thinking to sequences. The chapter challenges us with this. The sum of 4 consecutive numbers is 34. What are they? Through some logical deduction, we find 7, 8, 9, and 10. But honestly, more powerfully, we can use variables to represent any sequence. If p is the greatest of 5 consecutive numbers, the others are simply p minus 1, p minus 2, p minus 3, and p minus 4. By doing this, complex word problems become incredibly simple to decode. We aren't guessing anymore, we're mathematically modeling reality. Moving right along, let's dive into section 3, properties of divisibility. Okay, here is the absolute crucial point of this section, this core theorem. If A divides M and A divides N, then A will also divide their sum, M plus N, and their difference, M minus N. Let's make that a bit more concrete. If 2 divides 10 and 2 divides 6, then 2 automatically divides 16, which is 10 plus 6, and it divides 4, which is 10 minus 6. We have just proven a structural rule about how numbers are actually built. The textbook actually tests our understanding of this by asking us to evaluate statements as always, sometimes, or never true. For instance, if 8 divides 2 numbers separately, it always divides their sum. That's literally the rule we just learned. But what about the reverse? If a number is divisible by 8, like 16, does 8 divide any 2 numbers that add up to 16? Well, 9 plus 7 is 16, and 8 doesn't divide either of those. So that statement is only sometimes true, like in the case of 8 plus 8. Forcing ourselves to think about when these rules apply, and maybe more importantly, when they break, is how we truly master this stuff. Now that we've got the rules down, let's explore section 4, mapping multiples. The chapter asks us to imagine Venn diagrams for different sets of multiples. Just think about the multiples of 4, 8, and 32. Because 32 is a multiple of 8, naturally, all multiples of 32 sit comfortably inside the circle of multiples of 8. And because 8 is a multiple of 4, that whole circle sits entirely inside the massive circle of multiples of 4. Visualizing these nested relationships like this makes abstract number theory feel incredibly intuitive. And this brilliantly illustrates our core takeaways from the chapter. If A is divisible by B, all multiples of A are divisible by B. If A is divisible by B, it's also divisible by all the factors of B. And lastly, if A is divisible by two different numbers, B and C, it has to be divisible by their lowest common multiple. These are the absolute fundamental laws we've just visually and algebraically proven. They are the bedrock of the whole shebang. To wrap up our journey, let's see how these rules handle massive amounts of data in Section 5, the divisibility table. This table is where all that theory turns into pure magic. Look at a number like 990. In the past, you might have had to do brutal long division 9 separate times to figure out its factors. But by using our algebraic rules and divisibility shortcuts, we can instantly look at it and say, yep, it's divisible by 2, 3, 5, 6, 9, 10, and 11. We use the rule for 2 because it ends in 0, the rule for 3 because the digits add up to 18, and so on. It is a real game changer. And honestly, here's the best part. Even when the numbers balloon to over 600,000, like that 639,210 you see right at the top, the logic holds perfectly. The mathematical rules just do not care how big the number gets. This table serves as a really powerful mathematical cheat sheet, proving that once you understand the underlying algebraic structures, you can confidently decode literally almost any number you encounter. We've moved all the way from simple curiosity to universal algebraic mastery in this explainer today, but I'm going to leave you with one final question straight from the textbook to keep you wondering long after we finish. When finding the divisibility shortcut for 9, what property do you think the digital root will actually have? Think about the underlying algebra, test out a few numbers, and let your curiosity guide you. Thanks so much for joining me on this mathematical journey.